Okay, so hello everyone. Welcome to the discussion of the CMI Entrance, BSc Math Entrance 2023 problem solving. So we will talk about the subjective problems. They were really interesting. I have with me Raghunath sir from Chinta faculty team as well. So we will discuss two problems in this video, B1 and B2, and we are posting more problems and solutions and discussions in the link in the description, so you can check that as well. So let's get started with B1, the first problem. So the first problem is like this, that if you have it's given that n is odd. N is an odd number, so maybe it's 2k plus 1. It's of the form 2k plus 1, and we want to show, or rather it's given that n divides 2023 raised to the power n minus 1. This is also given. Okay, so n is odd and n divides 2023 raised to the power n minus 1. So our goal is to find such n, in fact smallest values of such n. two smallest values two smallest values of n that works. That's the first thing. We have to find two smallest values of n that works, and then we have to that uh, show that there exists infinitely many such n. That is, there are infinitely many numbers which has that particular property. Infinitely many numbers which has that particular property. So how do we go about showing it? Oh, n is greater than 1. Of course, 1 works trivially, so 1 is not that interesting. N is greater than 1, n is odd, and n divides 2 raised to 23 to the 2023 raised to n minus 1. So the first thing is this, that if you plug in the next odd number, the next odd number, that is n equals to 3. So we have to start with odd numbers which are greater than 1. So let's check with n equals to 3 and see what works and what doesn't. Okay, so the question is, does 3 divide 2023 whole cube minus 1? So we will easily see that it does. There are multiple ways of seeing it. You can do modular arithmetic. You can do that. You can also do a factorization of this thing, 2023 cube minus 1. So that would give you 2023 whole square, 2023 minus 1 times 2023 square plus 2023 raised to the power 1 plus 1. So this little part is 2022, and you can easily check that 3 divides 2022. For example, you can use the divisibility rule of 3. If you add the digits, 2 plus 2 plus 2 6, it's divisible by 3, so it's obviously divisible by 2022 is divisible by 3. There is another way to see that 3 divides this number. Well, 3 also divides the other part. Each of them is 1 modulo 3. 2023 is 1 mod 3. So 2023 square is 1 mod 3. 2023 itself is 1 mod 3. And 1 is, of course, 1 mod 3. So if you add up, then 3 divides that. So interestingly, 3 divides both of these parts, the first factor and the second factor. So 3 is another small number that divides 2023 raised to the power 3 n minus 1, where n is odd. So remember, we had to find two such numbers. Two such numbers.
The
Two
next
smallest numbers.
smallest.
So you have to find the next smallest number, right? The next smallest number. So Raghunath sir's solution will actually very easily give you the next smallest number that works. So I will not talk about the next smallest number. I would rather prove that there are infinitely many such numbers that works. Again, we have two solutions. I'll give you one and Raghunath sir will give you one. And both of these solutions are a little bit different, but they both give you two different ways of looking at the thing. Okay. So the first solution is 3, that works. The second next smallest number that works, we will hear it from Raghunath sir. And now I will show you that there are infinitely many such numbers n, such that n divides 2023 raised to the power n minus 1. Okay, how do I show that? How do I show that there are infinitely many such numbers, odd numbers, odd numbers n, such that n divides 2023 raised to n minus 1? Well, I will start with the fact that 3 divides 2023 square plus 2023 raised to the power 1 plus 1. 3 divides this number, right? We have already shown it. 2023 itself is 1 mod 3. So we can easily compute and check that the sum is divisible by 3. Now what we do is we write this as 3 times some q1, where q1 is odd. Q1 is odd. Why is it odd? Well, notice that 1 is an odd number, 2023 is an odd number, 2023 square is an odd number. So if you add odd numbers 3 times, in fact, if you add odd number of times, then the sum is odd. So this entire thing is odd. This entire thing is odd. It's divisible by 3 and the other factor must also be odd. So 3q1 is odd. So next what we do is we will work with 2023 raised to the power 3q1 minus 1. I'm going to show that this is divisible by 3q1. I will show that 3q1 would divide this. Why? Well, let's factorize this. This is 2023 minus 1 times 1 plus 2023 square plus 1 plus 2023 square up to 2023 raised to the power 3q1. So I have written down the entire factorization. This is simply the factorization of x to the power n minus 1, which is x minus 1 times 1 plus x up to x to the power n minus 1. We are using this factorization. Okay. So now what I'll show is that this part is divisible by 3q1. Why? Okay, let's check why. Let's write only this part. So 1
The
plus
last
0,
power is 3q1 minus 1.
3q1 minus 1, correct. The last power is 3q1 minus 1. So 2023 square up to 2023 raised to the power 3q1 minus 1. Okay. So I will split it into q1 parts. So the first part would be this 1 plus 2023 plus 2023 square. The second part will be 2023 cube 2023 raised to the power 4 2023 raised to the power 5. Okay, like this I will go on, and the last one would be 2023 raised to the power 3q2 minus 3 2023 raised to the power 3q2 minus 2 and 2023 raised to the power 3q2 minus 1.
So let's keep it as Q1 only, right? The
Oh,
exponent.
q1, correct, correct. This is q1, right? That is right. So q1. All right. So now each of these pieces is divisible by 3q1. You can check. How many pieces are there? Well, the total thing has 3q1 numbers because you started with 2023 raised to the power 0 and went out to 3q1 2023 to the power 3q1 minus 1. So there are 3q1 numbers in this. Each group has 3 numbers, so there are q1 groups in total. There are q1 groups in total. Now each of these groups is divisible by 3q1, that we have already shown. The first one is 3q1 itself. The second one is 3q1 times 2023 squared, because you can just take a 2023 squared common. Actually 2023 cube common, 2023 cube common, and so on. So this is 3q1 times 2023 whole cube, and so on. You can just keep on doing it. Each of them will be, this last one will be 3q1 times 2023 raised to the power 3q1 minus 3. So each group is divisible by 3q1. So the sum will be divisible by 3q1. Right? So we just showed that this part is divisible by 3q1. This part is divisible by 3q1. So this entire product is divisible by 3q1. So 3q1 divides this thing. Okay, now we can just repeat the same process. So now what we can say, okay, so since this part is divisible by 3q1, suppose it is 3q1 q2. This entire quantity is 3q1 q2, and q2 is odd. Why is it odd? Because again, we added up odd number of odd numbers. So this entire thing is odd. 3q1 is odd, q2 is also odd. So now what we can do is, and this I will leave as an exercise, that 2023 raised to the power 3q1 q2 minus 1, this is divisible by 3q1 q2. So now it's basically an induction proof. I'll just do the first step of this. You just split this up into 2023 minus 1 times 1 plus 2023 up to 2023 raised to the power 3q1 minus 1. So that's the first group. So you will keep on doing this group until you have all the terms, and it will exactly work out, and each of them will be divisible by 3q1 q2, Therefore, the entire thing will be divisible by 3q1 q2. So again, you can take the entire thing as 3q1 q2 q3 and do the same process again. So this shows that there are infinitely many numbers such that n divides 2023 raised to the power n minus 1. Now Raghunath sir actually has a much easier proof, and Raghunath, can you share your
Yeah,
screen again?
yeah.
Yeah.
So we were discussing about. Is my screen visible, sir?
No, it's not visible actually. Can you
Oh,
share the screen one more time?
yeah. Now is it visible?
Yeah, it is visible now. Yes.
Okay. So let us continue our discussion with proving the smallest integer n such that n divides smallest odd integer greater than 1 such that n divides 2023 power n minus 1. So Oshani sir has proved that n equal to 3 works. So this is a very small number. So this lets us to think to go to the further odd numbers, that is 5, 7, 9, 11. So let us try and check whether these are divisible by the divisibility works for these numbers. First, will 5 divide 2023 power n power 5 minus 1? It will not, because 2023 is congruent to 3 mod 5, and so 2023 power 5 is congruent to 3 power 5 mod 5. And so the entire thing is congruent to 3 power 5 minus 1, which is equal to 243 minus 1, which is 242. But 5 will not divide 242, hence 5 should not divide this one also.
Right.
Okay. 7 is very easy to prove. 7 will not divide 2023 power 7 minus 1, because 7 itself divides 2023.
Right.
So 7 itself divides 2023 per 7, and the consecutive numbers do not share any common factor except 1.
Right.
So 7 will not divide this. Now the next possible thing is 9. 9 divides 2023 power 9 minus 1. Let us check this. So 2023, what is this congruent to? Mod 9. It will be congruent to um,
Mm,
just the sum of digits mod 9. 3 plus
yeah.
2 is
Seven.
5, 5
Seven.
plus 2
Yeah.
is 7,
Seven mod 9,
7 mod 9.
which
Right?
is
Because
minus
any
2. Right.
number is congruent to the sum of its digits mod 9.
Correct.
And 9 then should divide 7 power 9 minus 1, because they are congruent. And 7 can be rewritten as minus 2. I mean, they are just congruent. Or you can directly deal here. 2023 power 9 is congruent to 7 power 9, and this minus 1 is congruent to 7 power 9 minus 1, and 7 is congruent to minus 2 power 9, and the minus 2 power 9 is minus 512 minus 1 mod 9, which is minus 513 mod 9, and
Which is,
513 is divisible by 9.
yeah, because the sum of the digits is divisible by
Is
9.
divisible by 9. Or you can factorize this to prove that it is divisible by 9 also, as we did for the case 3, case n equal to 3. So hence n equal to 9 is also a solution.
So the
And that is
second
the
smallest
smallest.
number, yeah, the second smallest number is 9.
Yeah. So now this lets us to think that 3 divides 2023 power 3 minus 1, and 9 divides 2023 power 9 minus 1. So what do you think from this?
Yeah.
So can we observe that powers of 3 are somehow divisible by 9? We don't know how, but somehow they are divisible by 9. Let us try to
Right.
make a claim on this. 3 power t divides 2023 power 3 power t minus 1 for all t in natural numbers. Obviously, the base cases are true, like t equal to 1 and t equal to 2. Let us try to prove this using induction, because um, directly jumping into that particular three party will be very difficult. So if you use induction, we have by the hypothesis that 3 power t minus 1 divides 2023 power 3 power t minus 1 minus 1 is true.
This is the base case.
Yeah, like this is the I would
Inductive
say
hypo Yeah,
uh,
inductive hypothesis.
induction hypothesis. This is my
The base
induction hypothesis.
Yeah, base case for t equal to 1 and 2 is like proved by hand in some sense. Yeah.
It is already done. So we are already completed the base case proof. We have just to prove that if it is true for t minus 1, it must be true for 3 power t.
Yeah.
And then it follows using induction. So
Yeah.
now let us consider the number 2023 power 3 power t minus 1. So this
Okay.
is nothing but 2023 power 3 power t minus 1 into 3. And this into 3 can be written as whole cube,
Right.
the whole minus 1. Now we know a cube minus b cube. It is 2023 power 3 power t minus 1 minus 1 into 2023 power 3 power t minus 1 the whole square plus 2023 power 3 power t minus 1 plus 1.
Right.
I know that by induction hypothesis written here, this number is a multiple of 3 power t minus 1. So this can be written as 3 power t minus 1 into some k naught into this bigger bracket. So let us prove that this one, the second bracket, is divisible by 3. So how will I prove this? Let us go to the number 2023 power 3 power t minus 1. We know that 2023 is congruent to 103 because its
Right.
sum of digits is congruent to 103. So
Right.
power 3 power t minus 1 is congruent to 1 power 3 power t minus 1.
Yeah.
And 1 power 3 power t minus 1 is again 1. So we know that this number is congruent to 1, right? So this, the whole square will also be congruent to 1.
Right.
And 2023 power 3 power t minus 1 is congruent to 1. And 1 is congruent to 1.
Right.
If you add up these three, this just gives us the second bracket is congruent to 1 plus 1 plus 1 mod 3, which is 0 mod 3.
Right.
So the second bracket is divisible by 3. So let us write it as 3 into k1. So as you could see, 3 power t into k naught k1 means the required number is a multiple of 3 power t, which proves
Right.
our induction uh,
Yeah.
step. So hence this claim is true. This claim given here is true. So you can put infinitely many values of t as it varies in natural numbers. So
Fantastic.
this
Yeah.
solution we were able to arrive for the first problem. So shall we continue about the second problem?
Yeah. Let's continue on the functional equation problem, the second one. Yeah.
Yeah, sure. So I'm going to paste the second problem and let us discuss this. So it is a function from natural numbers to natural numbers. So let us first note that we should not substitute 0, minus 1 or anything in place of m or n. So functional equation means the variables are our functions only. So f of m plus n equals f of m plus f of n plus mn into m plus n. Right? So first they are asking us to show that f is of this form and find the condition on the coefficients of that form.
Right.
So usually we tend to substitute n equal to 0 or m equal to 0, but not let's not do that because it's natural numbers. But instead, let us put
Positive
m
integers to positive integers. Yeah.
exactly. But we can put m equal to n because m
Right.
and n are any natural number, so they can be equal also. So
Yeah.
f of 2m equals 2 into f of m plus m into m is m square and into 2m, which simplifies to 2m cube.
Right.
Now, you will see something interesting if you put this is not m equal to n, this is n equal to n. And let's put n equal to 2n
Yeah.
because I can use this data to find f of 3m. So f
Yes.
of 3m will be, if you put that, you will get f of m plus f of 2m, which is 2 f of m plus 2m cube plus 3m square into, sorry, 2m square into 3m,
3m. Yeah.
which gives us 3 f of m plus 6 plus 2 is 8m cube. This is f of 3m. So this, like this, we can proceed. Right now, I will put 3m, n as 3m, and find f of 4m. So this is kind of giving us the value for f of km for any integer k. And my claim is as follows, that f of km equals k into f of m plus k times k square minus 1 by 3. This is my claim for all k in natural numbers. You will also be able to get this just once you proceed few steps, you will also be able to arrive at the conclusion that this is the function. You can now, we have to prove this.
There should be a k m cube there, or what? In
Oh,
the
yeah,
claim,
I
k into k square minus 1 by 3 times
oh,
something.
yeah. This should be m cube. That's correct. But yeah. That is correct. This should be m cube. Right. So now, how will I prove this claim? Because I just made the claim from nowhere. It seems like that. The proof is easy using induction. You can uh, claim that it is true for all k less than or equal to some t. Prove that f of, let's take that f of tm equals t into f of m
Right.
plus t into t square minus 1 by 3 into m cube. Now let us use the definition. Put n equal to tm in the functional equation. So to
Right.
get f of t plus 1 into m equals f of m plus f of tm, which is t into f of m plus t into t square minus 1 by 3 into m cube
Right.
plus
There was
this
mn.
part. Oh, sorry. There was the other part. Mn into m plus n, right? So
Right.
mn will be tm square. Tm square. M plus n will be t plus 1 into m.
Right.
So you will get this.
Basically,
So,
tm t into t plus 1 m cube actually. Yeah.
this is t into t plus 1 m cube. So taking m cube common,
Right.
you will get that t cube minus t by 3 plus t square plus t.
Right.
Right? So this just be 3t square plus 3t square plus 3t minus t will be plus 2t and by 3. So you will have t plus 1 into f of m plus m cube by 3 into you can take, you can write this as t plus 1 into you can take t common first and write it as t plus 1 into t plus 2, right? Now I will take the t plus 1 common. just factorizing this, taking t plus 1 common, and this is t square plus 2t. That can be written as t square plus 2t plus 1 minus 1, which is t plus 1 whole square minus 1. And this by 3 comes like this. And this proves the induction for t equal to 1. T equal to, I mean, for k equal to t plus 1.
Right, right.
So hence this is our claim. Uh, Now in our claim, let's put m equal to 1. If you put m equal to 1, you will get that f of k equals, let's put m equal to 1 here,
Yeah.
f of k plus k into f of 1 plus k into k square minus 1 by 3.
Uh-huh.
K into f of 1 plus k into k square minus 1 by 3. And this is true for all k in naturals, which we just proved by induction. Now, remember that the domain is itself natural numbers,
Right,
and f of 1 is a constant, and these
right.
are in their explicit form already. So we have already found the function in a sense.
Yes. So f
So
of 1 is some constant c, for example.
exactly. Let f of 1 be some constant in natural numbers, c suppose.
Right,
Then I can generalize this. If you take any f of n, that will be cn plus n into n square minus 1 by 3. This must be true. And
where
this
c
is
is
like an only condition. So what you can do as an exercise is substitute this back into the functional equation and check whether all functional equation of this form actually satisfies that condition, the functional equation. Every function of this form will actually satisfy the functional equation. So hence this is the general solution,
very
which is
nice.
1 by 3 n cube plus n into c minus 1 by 3. And the other question, the second part they have asked is find the necessary and sufficient conditions on these coefficients. You can find that very easily because c can take any value, any natural number value. So basically d must be 3, and you can take c3 to be 1 by 3 because this coefficient is 1 by 3. C2 and C naught are 0, whereas the C1 coefficient is C minus 1 by 3 for any C in natural numbers. Automatically C will be your f of 1 value. So that
Excellent. Yeah.
finishes.
That finishes the problem. Excellent. So, for the viewers, please go to the link in the description and provide us with the other problems from CMI entrance. We don't have all the problems yet. So, if you remember some problems, please use the form in the link in the description to share the other problems so that we can solve it together. Okay. And all the best for the upcoming ISI entrance, which is I think 7 days from us, 4 or 5 days from now. I'll see you in the next video. Thank you, Raghunath, for joining in.
Thank you. Yeah.